All right, in this podcast, we're going to talk about solubility equilibrium, which is synonymous with Ksp. All right, so we previously had discussed how we can predict whether a compound is going to dissolve in water or not using the solubility rules. They were very simple. If they contain ammonium, sodium, potassium, or nitrate ions, they're always going to be soluble. So we would write a little AQ next to them. All right, anything that didn't have one of those four in it, we labeled as the solid with an S, and we called that the precipitate or precipitate. All right, so that was most of the story. But what we didn't tell you was that those solids, they actually can dissolve a little bit. This is an equilibrium process. So because it's an equilibrium process, we can write an equilibrium expression for it. And we call the equilibrium expression for a insoluble salt the solubility product constant. So it's abbreviated Ksp. So that kind of helps me remember solubility product. That's where the S and P come from. So solubility product constant. All right, so just to reiterate, again, if you have a solid, you still have a little bit of dissolving going on, and this is described by an equilibrium process where you have some that are going in and being bound while others are leaving, and this can all be described by that expression. All right, so solubility product constant, Ksp, is similar to our Keq that we've previously used. So when we add a solid to the water, some's going to dissolve and split into ions while some remains a solid. So for the example of NaCl solid, we see it breaks into Na plus and Cl minus. Therefore, we can write the equilibrium expression for products over reactants. Since our reactants are a solid, we just ignore them. So you get this as your Ksp value. Okay. Here's another example. So you see that we have the lead 2 iodide solid. And I just wanted to put this example out there because it shows that stoichiometry is still important. So, of course, PbI2 breaks into Pb2 plus and I1 minus. There are 2 I1 minuses, though. So that has to be factored into the expression. So as you see down here, our expression, we're going to have that 2 on the outside there because of that stoichiometry. All right, so let's try just to practice writing a couple. Hopefully this is not too taxing. So it's basically just your ions, and then, of course, include the stoichiometry for the exponents. Okay, and then this one, let's see, we've got Ag plus, and there's a 2 in front of it, so a 2 goes there, and then SO4, 2 minus. And last but not least, we've got Bi, 3 plus, that's got a 2, and then we've got S2 minus, which has got a 3 in front. All right, so how do we actually calculate Ksp? So if we're told the concentration of any of the components of the salt, any of the ions of the salt, we can basically just use an ice table and back calculate to get our Ksp. Okie dokie, so if I go ahead and get my ice table set up. All right, so we are definitely starting with, we actually have no idea what we're starting with here. It's not going to be in our expression, so it really doesn't matter. And then this is 0 and 0. And then we know that this doesn't matter, right? This one is going to change by x, and this one is going to change by 2x. And we know that the concentration of the lead at equilibrium, which means saturated. Saturated means no more solid can dissolve. Okay, so that's equilibrium in this case. All right, so we know our lead ion is this 1.62 times 10 to the negative second. And if that's what that is, that's our x, right? So that means that if we just multiply it by 2, we can get our concentration of our chlorine. All right, so our Cl concentration ends up being 3.24 times 10 to the negative second. All right, now we just plug all this into our Ksp equation. Ksp equation is the Pb 2 plus and the Cl minus, and there's definitely a 2 out there. All right, so I'm just plugging these in to their respective places, and then that gives me my Ksp value. All right, so when I worked all that out, I got my Ksp value is equal to 1.70 times 10 to the negative 1, 2, 3, 4, 5, negative 5. All right, there's your Ksp. All right, now this question wants us to calculate the molar solubility from the Ksp. So this is kind of the opposite. So again, write your dissociation equation. So show how the solid would break up. So it would break up into Ca2 plus and CO3 2 minus. All right, so again, we don't really care about the solid. We don't really care how much we got. We're just trying to figure this out. So we got this, and then we got plus x and plus x. So our equilibriums are x and x. All right, y'all just excuse my dog hacking up a lung in the background. My bad. He has allergies. You know how that be. Okay. All right, so there is my expression. I'm running out of room. Okay, anyways. All right, so there's my expression. So basically, it's just x squared is equal to my Ksp, which is the 3.8 times 10 to the negative 9th. All right, square root that, and you get. So your x, which is your concentrations, end up being 6.2 times 10 . My dog's tail is hitting my medicine case. I apologize. 6.2 times 10 to the negative 5th, and we solved for molarity, concentration. All right, so when we're dealing with salts, they're going to have very small solubility product constants, or KSPs, and so you can compare the solubilities of two salts to try to decide which one might precipitate first or which one's going to be more soluble by looking at their KSP values. But this only works if the salts have the same number of ions. So see how you have CuI and CaSO4. If we wrote the dissociations for those, we would see that they each have 2 ions. So we can directly compare them. So now you just look at your KSPs. Because this one is larger, that means that it's going to go more towards the product side, so it's going to dissolve more. All right, now again, another example. We have 3 salts, okay? Understand that this one has 2 ions, this one has 3 ions, and this one has 5 ions. All right, so you can't really look at the KSP values here, because if you were, you would think that this guy right here, because he has, well, actually not that guy. I missed this other one. All right, based on KSP values, it would appear as if this one dissolves the least, then this one, then this one. But as you see over here, you've got calculated molar solubilities. This one, CuS, actually dissolves the least, then this one, then this one. So it's actually completely backwards. So the number of ions makes it very difficult for us to be able to look at the KSP to be able to make any predictions about molar solubility. So they have to have the same number. All right, so once again, they have to have the same ion to ion ratio, and then we can compare them. All right, here's another example. So here we have 3 ions, and there we have 3 ions. So we can compare these. So that means this guy right here, he's got a negative 49th. He is not going to dissolve very well, okay? So this guy got the negative 23rd. He's going to be the better dissolver between these two. All right, another one. Okay, so if you'll notice, all of these have 3 ions. Because they have 3 ions, we can compare them. So this guy right here, he has the largest value, so he's going to be the most soluble. All right, and then this one wants us to rank. Okay, again, you've got to count ions, right? So I've got 3, 2, and 3. All right, this one's a little harder because you have different ratios, right? So if you were to write out a ice table for these, you would notice that once you plugged it into the equilibrium expression, for this one, it'd be the Ksp is equal to 4x cubed. All right, now this one, because there's only 2, the Ksp is just going to be equal to x squared. Now this one, again, you have 3, so this one is also going to be 4x cubed. Now if you do a little math here, you can rank them very easily. Okay, so if you do a little math, you should be able to deduce some things. Okay, one thing, I got molar solubility here as 9 times 10 to the negative 5th. All right, now these two, obviously we know which one's more soluble here, right? Because you can compare them directly. They both have 3. So this one's definitely more soluble than this one. So we've just got to figure out where this guy falls in the mix. So we need to solve at least one of these to try to figure out where the other one goes. All right, little bit of math, and we see that this one's molar solubility is 7.5 times 10 to the negative 3rd. So far, this one is definitely the most soluble. Okay, so in order of increasing solubility, this guy would be the last one because he's the most soluble. All right, and then now we just got to figure out if the Ag2CO3 goes before or after. Like, is he better or worse? So a little more math. All right, and a little more math tells me that this one is 1.3 times 10 to the negative 4th. All right, so that tells us our order. So Ag2CO3, second most soluble, and then the one that is the least soluble is going to be our BaCO3. So, doesn't dissolve very well on this side, dissolves really well on that side.